What are you trying to do? What? It is full screen, no? Ah, yeah, yeah.
There are 2 files, 3 files are open.
Why is it open all the time? Okay. Stop sharing. Stop sharing? No, share?
Yes, sure.
Okay.
Will you give the mic? Put in the office.
Thank you. Baba. Okay. I'm really good.
And people online can ask questions.
Of course, no.
Unmute themselves.
I'm completely lackadaisical. Sure.
Okay, so people online can sort of unmute yourselves and ask questions. Anyway, so great pleasure for us to have an old friend of many of us in this room, Itamar Procaccia from the Weizmann Institute, to give our colloquium today. So Itamar, of course, is a specialist in what might be commonly called physics of complex systems. So his work spans statistical physics, nonlinear systems, fractals, chaos, a very wide range of work over several decades that many of us are familiar with and have used, many of us have used it in our work. And of course, Itamar's interests sort of span not just in physics, beyond. I mean, he has this sort of great curiosity and love for several things, which, history, literature, linguistics, a whole wide range of that, and a remarkable sort of zest for life and having a good time, which also shows in his work. And as I'm sure it will show in his talk. So Itamar, over to you.
So really, thank you very much. Really a pleasure being here. The last time I was in ICTS was for the review committee after the first 10 years. And I'm pleased to say that all the recommendations that we made there have been followed. So the place thrives. I'm sure it's because of the review committee. Anyway, it's really nice, except I have to say that coming from RRI to ICTS used to be easier in those days. Now it's madness. You know, you go on these roads and your guts appear in your mouth and oh my God. Anyway, besides this, great pleasure. Good food. The bed, by the way, in ICTS is too hard. So I didn't sleep well. I'm saying this for somebody to, I don't know, do something, put a mattress or something. Anyway, so what I want to discuss with you today is a dipole-induced topological transition, which you may know in other contexts. And all the other contexts, I'm going to stress this, appear in 2 dimensions. And I want to discuss with you an example that we found recently of such a topological transition in 3 dimensions in the context of amorphous solids. So before going to the actual context, let me give you a reminder of stuff that you may know, and if not, I'll try to just tell you briefly. So there are 2 well-known, 2 or 2.5 well-known dipole-induced transitions in 2 dimensions. One is the hexatic phase and the hexatic transition. It's a discovery that was made by David Nelson and Bert Halperin years ago, and I'll talk about this in a minute. And the other is the Kosterlitz-Thouless transition, which is a transition in the XY model. Originally, it was discovered in the XY model, where you have from a bound vortex, anti-vortex pairs at low temperatures. There is a transition to unpaired vortices, and vortices topologically are like dipoles, and at some critical temperature, and this has given rise to a huge amount of physics, topological phases, etc., and it was awarded the 2016 Nobel Prize in Physics to Kosterlitz-Thouless. So let me just remind you what is the hexatic phase transition, because what I'm going to discuss with you today, both in 2 dimensions and in 3 dimensions, is very reminiscent of the hexatic phase transition. So what is this? People before this discovery thought that a melting in 2 dimensions, 3 dimensions is going to be a simple transition in the sense that you have a solid, you warm it up, and then it'll melt. It turns out in the 2 dimensions, there is an intermediate phase that was not expected. And let me explain how it comes about. So in 2 dimensions, all lattices are hexagonal in equilibrium. So now at 0 temperature, you have an hexagonal lattice, perfect. And now you begin to increase the temperature a little bit, and you begin to see some fluctuations. So 2 hexagons begin to fluctuate and make a pentagon and a heptagon, pentagon, heptagon, like this, boom, boom. This is a quadrupole because they do fluctuate and create a quadrupolar field. Turns out the quadrupoles in this context weaken the solid, they say they reduce the moduli, but they are not breaking any symmetry. That is to say, the long-range order and of correlation functions, etc., long-range order, and also the hexatic order are preserved, even though you have these fluctuations which are quadrupolar. Now you increase the temperature a little bit further, and now in hexagon and pentagon become stable. So they're not fluctuating, they're pentagon and heptagon. This is a dipole. Now, a dipole has a very strong effect. It destroys, the dipoles destroy long-range order. They don't destroy the hexatic order. This is why the phase that you see is now called an hexatic phase, but it doesn't have a long-range order. It has only angular order, hexatic order. If you increase the temperature further, at some point the pentagon, heptagon bound dipoles separate into pentagon and heptagon. These are monopoles. Solids cannot support monopoles. So this is when the system melts. So before melting, there is another transition that is induced by dipoles. And there is asymmetry breaking. And you have part of the symmetry is remaining, translational order, long-range order, but is broken, but you have a hexatic order. The Kosterlitz-Thouless transition is basically the same, but a little bit more complicated with vortex under vortex, but it's essentially the same thing. So now these things appear only in 2 dimensions, and you want to ask why. Why do you don't see them in 3 dimensions? The reason is very simple. And the reason is that the energy cost of a dipole or a vortex, the same, in 2 dimensions, is logarithmic in the system size, in the area. On the other hand, what is the number of places where a dipole vortex can be inserted in a system? Well, of course, it's proportional to the area. The entropy is the logarithm of the number, so it's also logarithmic in the area. And therefore, the entropy is logarithmic in the area, and therefore, there is a temperature where there is a balance between the energy and the entropy, E minus Ts is 0, and dipoles become cheap, free, and they can be created. Okay, so this is why you have the temperature where you can see this transition. Now, what's the difference? That in 3 dimensions, this is no longer true. The entropy is still logarithmic in the volume because you can put this thing in so many places proportional to the volume, but it's not true that the cost is logarithmic in the volume, and therefore you don't have it. So there are no such transitions in 3 dimensions. So what I want to discuss with you today is what I think is the first known dipole-induced transition in 3 dimensions, but this is not going to be in the structure of the system. These are transitions in the actual structure of the material. I'm going to discuss transitions in the mechanical response of a system. I'm going to look at a displacement field that is occurring due to some external load, and I'm going to describe you as an example of a load. It's a very general thing what I'm saying, but I'm going to discuss an example of an amorphous solid that is going to be distorted by a load, and I'm going to look at the displacement field, and the displacement field will have these topological things that I'm going to explain, and it's going to show a transition in the response of the displacement field that is very akin to these things, and I'll argue to you why this occurs equally well in 2 dimensions, in 3 dimensions, etc. So I will consider a very simple setup, and I'm considering it mainly because I can do analytically everything. So I can do it in many setups, but let me stick to this also because I have already a prepared lecture. But this is a very useful thing because we've studied it very carefully and we have analytic solutions for everything. So we're going to think about an amorphous solid that is confined in an annulus between 2 circles or two boundaries of radius r in and r out, such that r in is much smaller than r out. And as I'll show you, the geometry affords analytic solution throughout. We've done it also experimentally. We did a lot of numerical simulations, but there's also an experiment, very nice one, that was done by my colleagues in Shanghai, Jie Zhang and Jin Chang. And the experiment is built with an outer boundary, as I said, and with an inner boundary that in focus looks like this. I will explain in a moment. And the yellow stuff is an amorphous material that is made of binary disks, of disks of 2 sizes in order not to have any crystalline order. And these are disks that have they are optically active in the sense that they rotate polarized light depending on how much stress there is there. So you can actually determine not just the position, but also the forces on them. It's a very nice system. I'm interested in this talk only about the position because I'm interested in the displacement field is going to occur. And what we are doing, we're going to inflate the inner boundary. So in the experiment, there is this gizmo that you could pull down. When you pull down, you get a larger R, and so R in goes to R in plus some additional D0, and so you force the particles from the center to go out, and you're interested in what is the velocity field that is going to be imposed.
It's a single layer of disks.
Huh?
It's a single layer of disks.
It's a single layer of this. So you can think about it as a 2-dimensional case, even though they do have a width. Bidispersed. In this case, it's bidispersed, but you do it also in polydispersed. It's enough bidispersed. So we impose a displacement. The displacement is that there is a displacement at r in that's going to be determined by this number d0, and it's in the radial direction, purely radial, whereas on the outer boundary, the displacement is 0. This is a hard boundary, so they can't go through. If you have this thing, now in this radial geometry, you expect that the displacement field is radial. That is, say, d sub r is going to be the radial component of d, and it's going to be directed in the unit vector r. And classical elasticity, if you believe that this system is determined by classical elasticity, the equation that you read, for example, in Landau-Lifshitz, is going to be this equation for the displacement field. So the radial component, the second derivative with respect to r, first derivative of r, dr over r squared should be 0. With the boundary conditions we have here, this is easily solved analytically. Even ChatGPT can do it. And the solution is that you expect a displacement field that's going to look like this. So when r is r out, this is 0. When r is r in, it is d0. And it should decay like 1 over r in the bulk and then go to 0 at the other end. So it looks like this. So this is in linear coordinates. It looks like this. This is what you expect, if elasticity theory were correct. Now, question, is it correct? Not always, not so. And in fact, I'm giving you already the bottom line of the lecture, and then I'm going to explain in more details. You find 3 different phases. So depending on the pressure. So if the pressure is very low, that is to say you have now this disk and are not even in contact, so you have a fluid. When you have a fluid, when you do a inflation of the inner boundary as explained, you're going to have an exponential decay. Let's say the influence is going to decay exponentially in the fluid. So in a log-log plot, you're going to get a linear line, and this is what you see also in the experiment. On the other hand, when the pressure is very hard, so you have in the middle, when you begin to compress, there's a so-called jamming transition where the system becomes jammed, and then when you compress further, the pressure is increasing. At sufficiently high pressure, we're going to see a quasi-elastic regime in which the solution that just discussed is realized. Let's say you do now the experiment, and you find that there is the same solution that I just show you with a log linear now show you, where the linear log show you now a 1 over r decay. In the middle, there's something strange. So in some intermediate pressure, and we'll have to understand what pressure, we have to understand when this phase is created and what is its meaning. In the middle, you have a response that looks like this. It looks complete. Now you look at the angular averaged response. The angular average response is a function of r, and it looks strange. It's neither this nor that, and I'm going to show you what it is. These are actually Bessel functions that are solving a different equation that I'm going to explain. But you see, this is the experiment. The line is a theory that has been solved analytically, and we have many examples, but the fits are no question that the theory fits. I want to explain what this is and what is the reason for the change intermediate. So this is still a solid. This is a solid, this is a liquid, this is a solid, this is a solid, but it's different response of the solid. And so I'm going to call it a quasi-elastic and an anomalous phase. And I'll describe what is the transition and why it happens.
What's the purple color?
Sorry?
What's the color in the center?
This is the direction of the particles in the displacement. Is it out or in? I mean, you see the funny thing that there is a negative part here. So you are pushing out and some particles are coming in. So it's a strange response in the sense that it's not what you expect from classical elasticity, where if you inflate readily, everything should go out. Oh, this is just displacement field. So you measure the positions of the particles before you inflate, positions after you inflate, and you take the difference. Displacement field always is not a space, is not a state variable. It's always with respect to a state or a reference state, with respect to a reference state. So all these, I mean, for some reason it doesn't show nicely. You could see this only red here and only red here, but it doesn't show. So I apologize. So as I say, now I'm going to argue to you that the intermediate phase is dominated by the existence of dipoles, and this is where we're going to connect to ideas like the Hexatic or the Kosterlitz-Thouless. No, there are order parameters in the sense of what fields we need to consider. Absolutely. So displacement field is only the only field, the only order parameter, so to speak, in the elastic theory. Now I'm going to introduce the other fields that needs to be taken into account. So if you want to think about it, it's like a Landau theory, which are the relevant variables that you need to. What I want to say that dipoles cannot be created locally, and I need to explain this. You see, you have to think about two different theories, electrostatics and elasticity. Now, you know very well that in electrostatics, you cannot create charges independently. You can create pluses and minuses. You put an electric field, you only can create dipoles. Let's say if you have molecules in your system, they can polarize, charges will go minus, plus, and you can create dipoles. Dipoles are all the basis of dielectrics. Now, dipoles in electrostatics are not destroying any symmetry, and the theory remains the same as in vacuum, except that the dielectric constant is renormalized. So dipoles renormalize the material parameters in electrostatics, and charges, when they appear like a salt in solution, go to screen the system in the Debye sense. So they change the structure of the theory. Instead of getting now dipole-dipole interactions, which are not changing anything, not giving spinning, if you have charges, they screen, and you get a Debye solution with an exponential decay with a typical scale. Elasticity theory, okay, so what we say in the jargon is that electrostatics protects monopoles, charges, but does not protect dipoles. Elasticity theory classically is understood that it protects both monopoles and dipoles. Why? Physically, it's very simple. If you try to create a monopole, let's say, for example, you expand, then the system will force you, I mean, without a force, you just try to do it. The system with the pressure will push this back, and you cannot maintain a monopole. You cannot maintain a dipole either, because if you take some particles and you move them out, then the Poisson effect will say that other particles will rush in from the other side, and you'll create a quadrupole. And truly, elasticity theory protects both monopoles and quadrupoles. Both monopoles and dipoles, but it can create quadrupoles like electrostatic can create dipoles. So the cheapest topological thing that can be created in elasticity theory is quadrupolar. And what I'm saying here, that I'll show you where dipoles come in, but they don't come in locally. They're going to appear as gradient of a quadrupolar field. I'm going to explain. So I just discussed the difference between elasticity theory and electrostatics. I hope that this is clear. In order to see the correspondence, just go one pole up. So what is true in electricity, monopole, dipole, now go one pole up to dipole, quadrupole, etc. So let me just show you that quadrupoles and dipoles really appear. So in this experiment, or in the similar experiments, we can just show this. So what is a quadrupole? A quadrupole is a topological thing that has this structure in angles and has a strength, maybe some Q that is multiplying this tensor. But this is how it looks in terms of the angular distribution. So it's a tensor that is traceless, and symmetric. Okay, traceless and symmetric, and has this cosine sine style. Now, a quadrupolar field is hidden where, when you do an experiment of this size or a simulation of this type, how can you find it? You have to find it in the non-affine displacement field. What is non-affine? When you do some external perturbation on a solid, amorphous solid in this case, there is the thing that you do, okay, and there is the response of the system, which is not the same. And the difference between the response and what you impose is the non-affine part. So how you get this? So for example, imagine that you measure in a system displacement field and you measure the strain field. So what is the strain? The strain is the gradient of the displacement. I don't know if everybody is familiar with elasticity theory, but think about the strain field as the gradient, the symmetrized gradient of the displacement. So you can measure it. If you know the displacement field, you can measure the total strain field. And now you want to subtract the strain field with a little a, affine. So you get now the non-affine part that I'm going to call strain field Q. So this is, again, it's a tensor, a second-order tensor, and now I want to analyze it. So what is the affine part? In this particular experiment is what elasticity would have done. So you now take the displacement field that is predicted affine by elasticity theory, you take the gradient, as I said, the symmetrized gradient, and this is what you expect to be the affine part of the displacement field, which you need to subtract. So here we know what is the affine thing. We have an analytic solution. Shows you why I want to use this example, which is rather simple, because I know everything analytically. I can compute now this thing. And now, when I'm computing this non-affine part, I'm going to multiple expand it. So firstly, when I do this, I'm not guaranteed that what I get is traceless. And therefore, I'm going to first take the trace. So I'm going to take this plus this plus this, 0, 0. This is the trace, okay? And now the rest, I'm going to see if I can write in the form of strength times a quadrupolar contribution. And how do I determine Q and theta? Well, since cosine squared and sine squared are unity, then Q squared is epsilon 1, 1 plus epsilon 1, 2 of the traceless part. So this is the TS. I took out the trace. So these components are the traceless, TS, and this is the Q squared. And the angle is nothing but 1/2 the arctange of this fellow over this fellow. Okay, so I can determine them. I have a displacement field. I can subtract the affine part. I can now take the gradient. I can do the multiple expansion. Why I don't have a dipolar contribution? Why the first thing is here quadrupolar? Because of what I explained. You cannot create dipoles freely in a matter, in a solid. So the first contribution over the unit tensor is going to be the quadrupolar tensor. Let me show you how it looks. It looks like this. Okay, so here is experimental determination of this quadrupolar field with the color code for the strength, and this is how it looks. And each pixel has also angle, theta. So everything is computable. And now the point that you want to realize is that this quadrupolar field is not uniform. This is where the frog jumps. Since the quadrupolar field is not uniform, there is now a dipolar field that comes from the gradient of the quadrupolar field. So when you have a quadrupolar field, the gradients thereof is a dipole. And we can prove it very easily. You do an integral over, you get Berger's result. Everything is topologically well set, and you can find a quadrupolar field, and this is how it looks. So you now take the gradient of this one, and it looks like this. When you expand, looks like this. The projection is not that great. Now this is a vector field. This is now the color code is for the scalar magnitude of the dipolar field, and it has a vector for the direction. So this is now a dipolar field. So what I wanted to show is that we can take an experimental or simulation system and explicitly show that there exists quadrupolar dipole field. And I still maintain this is in the response, in the displacement. It's not in the material. They say the material is amorphous. It remains amorphous. You see nothing. You just see, okay? But the dipolar field, the displacement field begins to show these topological interesting things, which we're going to make use of. So dipole fields, I say, is interesting, and I refer again to that they are associated with symmetry breaking, and I'll be more explicit, Kosterlitz-Thouless transitions, Hexatic transitions, etc. So we need to now understand how to take the theory and include these things in a sensible way. So already in 2021, we had, no, this actually before. So, we know already for a while that the quadrupoles, even when they are uniform, they're going to change the energy of the system. In what sense? So that the energy of the system now will have the elastic contribution. The elastic is always the strain times the stress integrated over the system. But now there is a quadrupole interaction, when you have this, and you have the interaction between the quadrupolar and the background field. And this we already wrote in 2012 when we try to understand shear bending instabilities and things like this. So there is a cost to the creation of a quadrupole because of the background elastic field, and there is a quadrupole interaction up to quadratic order. I'm going to do a theory now in all the Lagrangian, all the Hamilton, in all the energy functional and all Lagrangian, and we're going to go to quadratic order because it's sufficient for what I'm going to describe here. In general, if you have instabilities, you may want to go further. Okay, so in symbolically, I'm going to write the elastic part as the elastic tensor here times the strain. Now the strain is U. Before it was epsilon. I apologize. So A alpha beta gamma delta U alpha beta. This is the strain gamma delta. This is, I'm sorry, together this is the stress gamma delta, and this is the strain gamma delta. So stress times strain. This is the usual thing. This is Landau-Lifshitz. Landau-Lifshitz stops here. And then I'm adding the quadrupole interaction with another coupling tensor, and I'm doing the quadrupole strain interaction with a third tensor. Oh, by the way, all these tensor can be written explicitly. I don't want to bother you with technical details, believe me. Now, what we want to do, like Landau-Lifshitz minimizes this energy functional, and the Lagrangian is going to give, when you minimize this Lagrangian, you're going to find the equation for displacement I've written before. Now, I'm adding these contributions, and I want to minimize the energy again, and I want to see what is the equation. To our surprise, we found that we get the same equations that Landau-Lifshitz get, but with renormalized elastic moduli. Let's say, like what I told you in electrostatics, there the dipoles renormalized the material parameters. So here, the quadrupoles by themselves only renormalize the properties of the material. They're not changing the structure of the theory. Okay, so you still get the same equations, but with renormalized moduli in A. So A gets renormalized, but there's no, and I don't want to show the details, but believe me. So as I say, this is a situation analogous to dielectrics. So what it forces you is to add reference to the dipoles. So the dipoles are there when you have the gradients, the effect of non-uniform density of quadrupoles. Now, I assume that the elastic tensor is already renormalized, so I don't need to take into account the quadrupoles. And I'm adding now the contribution of the dipoles. So there's a dipole-dipole interaction, and there's a dipole density interaction. These are all the quadratic terms that are allowed by symmetry. If you want to go nonlinear, you have to add further terms, but I'm doing it to quadratic order. And I'm going to minimize this Lagrangian. And when I minimize this Lagrangian, I get a new equation. So instead of the equation of Landau-Lifshitz, which in Cartesian coordinates is looking like this, so Landau-Lifshitz we will write this equation equals 0. Now there's a new term gamma d that appears because of the appearance of the dipoles. And I cannot overstress how much this additional term is changing life. Firstly, you realize that this is a scandal. And when I showed this equation to colleagues at the first time, they said it's wrong because it breaks translational symmetry. Right? In elasticity theory, displacement field always is protected by gradients. Why? Because if I take my system and I move it from here to here, the displacement field has changed, but nothing has changed in the system. So you are used to the fact that a displacement field appears with gradients protecting it, so a uniform translation will do nothing. So it does. It's here, and it's break translational symmetry. And it does. There is broken translation symmetry, and as I'm going to see later in the consequence of this. Now the question is, what is this coupling tensor here? So at the beginning, when we were developing this theory, we had no idea. So we said, look, it's isotropic system, it's homogeneous. Let's assume that this is that this tensor is diagonal. It turns out that simulations and experiments taught us that this doesn't fit and is not true. And in fact, the new tensor has to be written in this way. So at the beginning, we thought it was just diagonal with kappa squared, kappa squared. You see that this gamma has to have the dimension of 1 over length squared. So these are now screening coefficients that kappa is inverse length scale. So you have here kappa squared, but also you have non-diagonal terms, and the non-diagonal terms are asymmetric. And this all experiments, all simulations indicate and force us to go to this form. So in some systems or in some realizations of the system, there is a minus kappa squared, kappa odd, we call it kappa odd squared, and plus kappa odd squared. In other system or other realizations of the same system, this is a plus and minus, and this is a breaking of chiral symmetry. That is to say, you can see this in the simulations. That is to say, one can show that if it's only diagonal, then the dipole field and the displacement field have to be anti-parallel. It turns out there's always an angle between them, but the angle can be this or this, and it's this or this. It's not half and half. So there's a breaking of chiral symmetry. When you have breaking of symmetries, like the Noether theorem that I think that we have, are we speaking here in the Noether room, or this is the Noether seminar room, right? So it's appropriate because the Noether theorem says if you break a symmetry, then you lost a conservation law. This is where plasticity comes in. You broke symmetry and the system loses energy conservation. You can have plastic responses. And this is what is giving rise to this quadrupolar dipolar business.
So in the experiment you showed happens 3 phases.
Yeah, so at large pressure, and I'm going to explain why at large pressure, the system is elastic or quasi-elastic in the sense that if you do inflation, deflation, you're going to go back to the same position, same displacement field. Once you've broken into the new phase, you do inflation, deflation, you're not going to go to the same system. You're going to have an energy loss. Energy loss or energy gain, depending on minus plus or plus minus. You can store elastic energy or lose elastic energy, but you're not energy conserved. Sorry?
Time translation in gradient, that is not being broken yet.
No,
So then
there's no time.
why energy?
No, but there is no time.
Since the time translation Hamiltonian is the same, it is not changed. Why is the energy being
Hamiltonian has been changed now. You are now have a new energy form, right? The energy is no longer stress times strain. The energy now is different, okay? So you've changed the energy functional. Okay, now the anti-symmetric components, as I say, are responsible for irreversibility energy dissipation. And okay, so now let me go back to the general picture and then explain a little bit more. What are the symmetries that are being broken? So as I said, there are 3 phases: liquid, which is unjammed; solid, which is quasi-elastic; and intermediate. So I go back to what I showed you before, but now I want to say a little bit more. What are the symmetries here? What are the symmetries here? And what is the symmetry here? So firstly, here we know in the liquid that there is no symmetry, no rotational symmetry, no radial symmetry. It's a liquid. And as I told you, when you inflate here, you have an exponential decay. Now, but what is the exponent? So the exponent, when you now begin to increase the pressure, the length scale is increasing. That is to say, the effect on the fluid goes further and further out. So what you see is that you have a typical scale psi that is increasing with the approach towards the jamming transition, and these are for different system sizes. You see that it's increasing more and more in a more and more clear way, and this is well known. The jamming transition has been studied for the last 20 years very carefully. People know that there is a length scale that is increasing to infinity when you go to the jamming transition, and when you become a solid and not a liquid, and therefore now you're going to have an effect that is going all the way. So this is phi is the area fraction. So the area fraction is how many particles per unit area. So, and the pressure, as I'm going to show you, is a function of this phi. This is psi. Psi is the influence length. So when you do this exponent, it goes like e to minus r over psi. What is psi? Okay, so psi is diverging when you go to the jamming point. It's well known, and people know how it goes and exponents and everything. Now, the question is what happens on the other side? So once you're in, I'm going to argue that a length scale goes up, will go down on the other side. I'm going to tell you how and how it comes out in terms of theoretical thing. But that's going to be crucial because the decrease of this length scale is going to explain where the transition is going to occur. On the other hand, when you are in the elastic regime, we have an analytic solution of everything, including the angular direction. And all the solutions that are allowed are the so-called Michel's solution. Mr. Michel, a French mathematician, has classified all the possible solutions in this radial geometry, and they're all cosines and sines of the angle. So being cosines and sines of the angle, here you see in experiment how it looks. You can predict what you have in all the angles. You have a long-range correlation in the angle, and you have also a long-range correlation in the radial in the sense that you don't have exponential decay, but the power. So you have two symmetries, radial and tangential. The tangential symmetry is what you lose when you go to the thing here. And I'm going to show you that when you come from this phase, when you come from this phase to this phase, the angular correlation length is going to diverge, is going to look like this, and we determine exponents, we determine all kinds of things. So what is going on is that here you have both angular and radial symmetries. Here you have none, and here you have broken the angular, but you still have the long-range radial in the sense that you don't have an exponential, but you're going to have something else. Okay, in 2D, this has been shown already last year, and in 3D, it was published only recently. The fact that you have also such a transition in 3D. Now let me go a little bit in detail if I have more time. How long do I have? I do have more time, right? So 3 dimensions, how do you show this? How do you show the divergence? So it's standard analysis in the sense that you look at the radial component of the displacement field as a function of position and two angles. You have, you Fourier transform, you average. I don't want to go into many details. So you have a correlation function. You plot it as a function of this f, and you see all these solutions as a function of the pressure. And there is a critical pressure where it goes like a power. So you take this correlation function, you write it as a generalized Lorentzians, you fit it, all these lines are the fits to this form. And a power law is when f star goes to 0. So when f star goes to 0, you define a correlation length goes like 1 over f star. And then this is what I showed you before, that the damn thing is diverging towards a critical pressure that I still owe to explain what is this critical pressure and how it is selected. So we find from numerics that the way that it's diverging is with exponent mu. We have no idea theoretically why mu is this form. It could be 1 2/3, I don't know. We don't have a theory for the exponent. We don't have any renormalization group for this thing. And you can see these numbers and the analysis in more detail in this PNAS that was published a couple of weeks ago. This is 3D. Sorry? No, I do a sphere. For this example, for the inflation mechanism that I'm studying here, instead of doing two rings, I do an outer sphere and an inner sphere, and I inflate the inner sphere. All the rest is more or less the same. And the analysis is similar in 2 and 3D. So where to expect the phase transition? What is the critical pressure? For this, I need to say a few more things. I didn't go much into the analytical solutions of the equation that you get with the effect of the pressure. Let me tell you that they look like Bessel functions. But these Bessel functions need to fit boundary conditions. So this selects what are the possible screening exponent, those kappa even, kappa odd, in the sense that when you look at the possible solutions as a function of kappa, so this is here the screening exponent, the screening parameter kappa, then there are these special positions that the system can respond with that kappa. Now, as I'm going to argue to you, there is a transition in the sense that for large pressure, this is the logarithm of the pressure to -1, the effective kappa is going to be 0 because none of this can be expressed for reasons they're going to explain. And then there is the first pressure when you can express one of these solutions, then you jump to that thing. So I'm saying this is due to boundary conditions, so the allowed values of screening parameters are determined by the geometry, not by the pressure. The only question is whether the system can express those solutions or not. So then what we're going to go is remind you or tell you, those who know, a little bit about the jamming story. So in 3 dimensions, you know that systems will jam when the number of neighbors is 6. It's according to the Maxwell theory when it has to go like twice the dimensionality. So in 3 dimensions, when the number of neighbors z is 6. Now, when you are within the jam thing, z is larger than the critical one, which is at the border, and they call this the delta z. And it has been argued already before, not by us. It started with Sid Nagel and Andrea Liu, and then a lot of work, Mathieu Viard, lots of people. So the pressure is increasing like delta z cubed. So this is known. Now, the point is that you want to understand a length scale. So you now ask, when I have a positive delta z, how many cuts I can do without the system collapsing? When you are at the borderline, you just jammed. So if you now cut one connection, the system will collapse. And I want now to argue to you that when the system will collapse is what is a plastic event. As you say, a plastic event is a collapse of the system, could be the whole system or a part of the system. And I want now to estimate what is the typical size that I can have of plastic avalanches. What is plastic avalanche? You do an inflation in this case. Some connections are going to change, and because of this, boom, part of the system is going to become plastic and not going to be this, and going to be rearranged and regain its rigidity. So you know that when you have, so you can cut a whole circle with so many neighbors, a whole circle of length L, if you have enough delta Z times L to the minus to L to the D. So this is how many cuts you can do without collapsing the whole system. And this is already an argument by Viard, Nagel, and Witten 20 years ago. And the result is that you predict a length scale that, as I said, decays now like the pressure. As I promised you, you had a length scale that is diverging towards the jamming, and now there's a length scale that goes on the other way, and goes like p to the minus a third. Now what I'm going to argue to you, that this is a very important length scale for our discussion, because when pressure is very high, this L is very small, so typical events, typical plastic events are going to be minimal. And they are not enough to give you gradient of the quadrupolar field that's going to be of the order of the screening length kappa that the system wants to express. So what I want to say that the transition occurs where your preferred kappa to the minus 1 is about L. And you now can estimate from previous theories how L really goes like delta Z. This is this paper here of these friends from Holland. And what you find is that indeed the delta Z goes like a power, you fit the parameters. And in our case, you find the delta Z goes like 1.15 times p to the third. And therefore you estimate the PC from all these things to be 2.41. It goes bingo where we see the transition to within a couple of percent. So I think this is the physics in the sense that there are typical scales that are there, and what is the typical scale of plastic deformations that are going to occur, which are going to allow you a quadrupolar field that's going to have a gradient that is sufficiently large to express this kappa, and this is where the pressure is going. This is where the transition is going to occur. So a summary. Sorry? Which one?
Last quarter.
Here? So now I'm asking, I know what is the kappa, okay? I know what is the delta z. So now I have now the exact delta z with parameters in front. I knew from before that it's going to go like p2 to the third. I didn't know what is this number. So we measured in our case what is the delta z, and you have this number. And now you say, okay, so when L is going to be like kappa. So I'm asking when kappa to this 1 is L, and that pressure that I'm going to get from here with delta z is the PC. Okay, and it fits very well. And it fits not just in this experiment, in all the cases that we looked. So what we discovered intermediate phase in the jammed amorphous solids between quasi-elastic and liquid. And again, I want to stress, it's not a transition in the structure. It's amorphous, amorphous, amorphous. It's just a transition in the mechanical response due to external strain. There are two sharp transitions between quasi-elastic and anomalous, where angular correlations are lost, but with remaining radial long-range order. Between anomalous and liquid, where also radial long-range is lost. The values of screening parameters and the pressure of the transition are theoretically predictable. Remaining questions for the near future, coming back to you, is really to solidify it even better the relations of the anti-symmetric screening parameters to irreversibility. I think I gave you an answer, but it's not complete. And I think we need to go a little bit further to understand how it goes. You know, in some sense, it's crazy because, you know, we are starting with a Lagrangian and energy, and then we say, really, energy is not conserved. So there is some phenomenological step here that we've taken that needs to be maybe improved. And I thank you very much for your attention. Quiet.
Questions?
Chandan.
So is this a general feature of jamming phenomena, or I mean, nothing?
I think it's a general feature of amorphous solids. Mm-hmm. That is to say, amorphous solids have a tendency towards plastic responses. Let's say, because of the complicated energy landscape, they're always close by minima in the energy landscape that become easily available. So you do something, and the system will reorganize. And the reorganization is the plastic event. Also, generic is that plastic events are always associated with quadrupolar topologies. Yeah. The displacement field, this is the cheapest way to release stress locally. Once you have quadrupolar fields, and if they're not uniform, you'll have gradients, you're going to have dipoles. So that, I think, is generic. And it's going to appear, and we showed it already in system under shear, we showed it in systems other, you know, we have an exact solution for a spherical cap that you push onto the plane, and all these things repeats in the very same way. What will happen, for example, when you start to have more complex materials? You know, you add polymers, you add activity, you add God knows what, you know, what's so popular these days. One needs to rethink. This is really the simplest possible non-elastic or the post-elastic kind of thing. Amorphous solids, zero temperature, no time, so the quasi-static, either one step of strain or quasi-static, you know, step by step. That we can do, and a quadratic order in the Lagrangian. So it's the simplest thing, and you see how much surprising things we discover. You know, this is why in the previous conference last week, I told people, please tell me about the simplest examples of what you want to have in mind. You want to do activity, don't do activity with gamma dot and with temperature jump and this, because, you know, langsam, you know, there's so much to discover also in the simplest thing because it hasn't been done. So we need to go slowly and do things in a systematic way.
If you look at the simplest, I mean, just hard spheres or something like that.
Hard spheres I don't like, I'll tell you why. They're very singular. Mm-hmm. And I think hard spheres have, even though they're used very efficiently and cleverly in the context of mean field theories of glass transition and things like this.
Hot spheres
Yeah.
can be solved exactly. So
In the infinite dimensional limit.
Right.
Yeah, infinite dimensions, then you assume the same thing is in any d dimensions, and some cases it works. For example, for the jamming, it worked beautifully. But I don't think that for plasticity it worked as well. And I don't think that it really matters. You see, what we're doing here is a field theory, so it's a long wavelength theory. Whether the interactions locally are Hertz or Lennard-Jones or hard spheres, I don't think matters. And we show that all these things appear in all these cases. So it doesn't matter really what is the local interactions. It's really the conservation laws and the typical responses of amorphous solids, and the topology wins. So you always have these quadrupolar effects in the displacement field, and then you can proceed with the theory of this kind. If you want to do instabilities, and we are doing, so for example, the phenomenon of shear bending, when you shear, then suddenly there is all the shear is concentrated in one region, and the system breaks. For this, you need to go to further order. We have to go to, according to what I think, we have to go to quadratic order in the dipole. But we also have to add the nonlinear interaction between the strain field and the displacement field. So here I've used the strain field as the symmetrized gradient in displacement. For that, you need to also add the second order term, the grad D term. And then I believe that we will be able to offer a theory also of the instabilities of shear bending within weeks. It's already being written down.
Okay.
Deepak.
Local structure of the quadrupoles. The local structure of the quadrupoles, is it two small spheres and two big spheres or some such thing?
No. I mean, it's the local structure has to do with how the particles are streaming. So some are streaming out, some are streaming in. Okay, so this is how it looks. You know, in some contexts, this is known as the Eshelby inclusion. I don't like it, I'll tell you why, because people have used very small systems to show, including me, people including me here, it's a very small system to show single quadrupoles, and they appear. If you take a small system and you shear it, the first plastic event is a single quadrupole. Now I want to do a long wavelength theory. So I'm much happier with the quadrupolar field. And for this reason, I developed this little trick that I showed of the multiple expansion of the field, where I can have a quadrupolar field, but you don't see singular quadrupoles. You just have a quadrupolar field. Rama.
I'm just trying to get an intuitive feeling for this.
Good. I was trying for 5 years. Yeah, go ahead.
So, like initially, you in your experiment, you put a bunch of these round particles there, and they're kind of close packed. Like there's lots of them.
So as I say,
fraction they occupy.
that depends if it's below or above the.
In the liquid phase.
In the liquid phase, their density or the area fraction is below the jamming. They are not jammed.
But it's like somewhere in that vicinity, right? Like because you squeeze it a little bit and something changes.
Yeah.
Okay, that's not even important. The important thing is that you have this narrow window where things are different from either the elastic or the liquid.
It's not necessarily narrow. It depends
it's
on
not narrow?
Not necessarily. It depends on the properties. Let's say it depends on the exponents, how the length scale depends. So for this particular case of the inflation, it is relatively narrow, but not very narrow. You know, you don't need to go microscopically close to the.
So are you saying that in this intermediate phase, there are things which became, let's say, things started out as hexagons more or less in the solid phase, and they became
No.
pentagon and this?
Again, I stressed, I think 3 times. It's not a transition in the structure.
Okay.
It's not the structure of the solid. The solid here is anomalous before the inflation, is amorphous before the inflation, amorphous after the inflation. There are no hexagons in the structure.
It may not be exact hexagons.
No, there's nothing.
Changing in that nearest neighbors or something like that.
There is going to be responses, and the responses, which is the displacement field, is going to exhibit topological defects. And the reason for this is, as I said, is the conservation laws that elasticity does not allow neither monopoles. You cannot have something like this, not dipoles. You can't have just like this. So the cheapest thing are quadrupoles.
Yeah.
So the response is, the plastic response is going to be made from quadrupoles. And then you get the dipoles of the gradient of this field.
But surely visually, if you look at it, you'll see something there.
You see things moving. You see things moving. And you see a displacement field. The displacement field is measurable. You can measure it and you can now analyze it. But you cannot see, I mean, I don't know anybody who can tell what was before and what was after. If I just give you the two pictures, the equilibrium, the mechanical equilibrium, forces are zero, torques are zero, and it's amorphous. So how do you characterize amorphicity? We discussed it. We don't have many techniques to quantify disorder. We have beautiful techniques to quantify order, symmetry groups, all these things, right, but not disorder. So it's disordered here, disordered there, it's amorphous here, amorphous there, and the only thing that I have a handle on is the displacement field that I get from comparing between the present state and the previous state. And also strain is not a state function. Also strain is only defined with respect to a reference frame. Stress is a state function. The stress I can compute from the forces and the positions. There is the virial theorem. I can look at the system and compute its stress. But all the other quantities are with respect to a reference frame. And this is why I don't know how to do this thing well if you have a time-dependent thing, because I don't know what reference state I have to do this with respect.
Okay, so finally, are these states just a function of the area fraction occupied, the number of particles?
The area fraction determines the pressure. And as I said, the pressure determines the typical length scale that appear. And the geometry and the pressure are talking to each other.
So in principle, I mean, except that you want to connect it to the previous phase, in principle, I could make a geometry which doesn't change. I don't inflate or something, but stuff the right number to get the intermediate phase.
No. The intermediate phase is a mechanical response to something. So, if you just make a phase at that particular pressure, then what? It's an amorphous phase. What can you say? It's in the response. It's in the mechanical response. I'm saying it again and again and again. It's not in the structure. You're not going to see it in this equilibrium structure. It's an amorphous solid. Now you have to do something, shear it, spit on it, kick it, something. And now analyze what is the mechanical response with respect to the reference state. Very crucial.
Got it.
Okay, this is why we have this additional new thing that we can see it in 3 dimensions. That our dipoles are not in the structure, because dipoles are not going to work if it were in the structure, because that's only in 2D. Because this is a gradient of quadrupolar field, then we have these dipoles that are making the whole game happy.
Yes, a small thing. So could you tell once more what's the intuition to think about the breaking of the translational invariance, which was coming in?
Well, once you have gamma D, then D is not protected by gradients. So apparently, if you just move the data system, D changes. So that is a clear violation of translational symmetry. Now, the violation of translational symmetry is equivalent to having screening parameters, which appear. So the screening parameters have to appear once you've broken the translational symmetry. The oddness in the gamma there is because you also broken the angular chiral symmetry. As I showed, you really break the angular symmetry in this case, but also in all the other cases. So then you get this off-diagonal thing. I don't know, some of you may have been aware of a recent progress in elasticity theory when people are talking about odd elasticity. This I want to call odd plasticity. But it is very reminiscent in the sense that you now have odd plasticity that is responsible to breaking of symmetries in a similar way as odd elasticity is due to symmetry breaking in the other case. You raised hand? No, you didn't raise hand.
No, so just wanted to know
you-
whether this shows up at all in the
Sorry?
elastic constants. I mean, this.
The elastic constants are in the A tensor okay, and they are being renormalized by already by the quadrupoles. So the quadrupoles renormalize, and we have explicit forms how A is renormalized by all these tensors. And indeed, when you do quasi-static, you see that your stress is increasing with different slopes. So we can now predict really how the slopes are going to change by following in each point how the elastic tensor has been very renormalized, if you want to do this.
No, so when you go from the liquid to this intermediate phase, the shear modulus has some jump or something like that, or is
It is growing continuously as a parallel in delta Z.
so okay?
Yeah, this is well known. This is well known. I think the more exciting thing would be in the nonlinear case when you have a big drop in the stress and you have a real shear bend, where now sort of as if you can increase the stress a little and the strain will just not be able to support it. Effectively, you're going to go to zero shear stress, shear modulus. That is going to be a much stronger effect that you are going to need nonlinear stuff in order to understand and explain. Yeah, Abhishek.
Yeah, so I mean, after including this quadrupolar energy, you got the modified equation for the displacement field.
After including the dipoles.
Yeah.
Yeah.
And does this reproduce that intermediate displacement versus?
Oh, sure. I mean, you can solve this equation analytically in this case and in other cases that we've done. And the analytic solutions, I didn't want to bother you with technical details. They're usually expressed in terms of Bessel functions, J1, Y1, blah, 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 and that have to fit the boundary conditions. So, you have almost classical quantization in the kappas because you need to solve this with boundary conditions. So, but you can solve it analytically. It's actually not hard even.
It reproduces the experiment, whatever you showed.
Yeah, it's all analytical. All analytical. I don't need to do any numerics here. Everything is analytical. Well, of course, the analysis of the simulation of the experiment is numerical, but the theory we can solve analytically all the way, including for the nonlinear theory that I'm developing now. I mean, surprisingly and shockingly, we can solve analytically even in the nonlinear case.
Even 3D.
Yeah, I mean, GPT suddenly makes everybody very powerful. No, actually, I learned it only 3 months ago when I was in Singapore and I was working with Massimo Picacciamara. And I developed a normal form that gave a differential equation. I asked Massimo, do you have a student to analyze this? So he said, what do you mean student? Let's ask GPT. I said, what? And you put the thing and it solves it. Then you ask plot it, then it plots it. Then you say write it in Tech for the paper, and it's done. So in 20 minutes you get the work of a student for 3 months. I mean, it is pretty shocking, I have to say.
We edit this out.
What?
So Jonathan, the referee reports will also be generated the same way.
No, I actually really mean it. Those who don't use it, Mathematica is tough. It's hard to use. This, you can just ask him in words. Please do it. And at the end, he says, thank you. ChatGPT. Yeah. Yeah, after he's done my work.
Thank you. We can have other questions outside of the hobby. Thanks so much.
Okay, thank you.
So that's nice. It works for you, and then thank you for letting me work. But that's too far, you know, you probably haven't seen. The structure is.
So, Itamar, nice to see you. I'm going home.
Same here. It was nice seeing you. Okay,
But you're leaving on Wednesday or
on Thursday. So I'm going to be here also on Wednesday.
Wednesday? And next-
So if you come, I would love to hear what you're doing and your. I always respected your out view of stuff. So I'd be very happy to hear what you're
Yeah.
doing. I don't have any students either, but I have collaborators all over the world. So I'm happy. And besides, not having students means that I can think. You know, I don't need to come up with 6 new ideas every day for all the students, you know, so it's very useful. Yeah. No, it's a lot of stress to have all these young people to take care of. I know.
That's very nice.
Thank you.
So you use the paid one, I guess, ChatGPT?
Yeah.
The ChatGPT 4.
Actually, I'm also using Gemini, but for different reason. No, Gemini surprised me. You know, I have a problem a little bit with my spouse these days. She had pains in the calf. And when doctor after doctor after doctor, each sent her to this test, MRI, CT, some 20 tests, 20 doctors. Everyone takes a fortune for the 20 minutes anesthesia, and none came up with an answer. So then I said, look, let's take all these tests and feed it into Gemini. And Gemini said the problem is there. And this morning she got a shot where Gemini said the problem is, and she just called me. She's expecting to tell me tomorrow, did it work or did it not? Ah, thank you. Sorry.
Can
I almost told you.
you just?
Yeah, yeah. So
You fed in like X-ray reports and like what did you? Just report.